All right, so 6.1 to 6.4 is the test this Friday. We need to consider the fact that it's mainly energy with a little bit of power at the end, right? That the whole topic is about energy and work, and then we kind of took yesterday and talked about how power is a result of energy or work in a given time period, right? In a given time period. So that's the only difference that we have between power and energy, is that power is a function of time. Energy is not a function of time. I can take as long as I want to lift an object over my head, and I'm still giving it the same amount of potential energy. Even if I lifted it faster, it's the same amount of potential energy. But the power generated is different. Power is a function of time. Energy and work is not. So that's the general idea of this test. I expect it to be something that you guys do well on. It's not one of the harder topics of the year for sure. The multiple choice is not like a tricky kind of test where you're going to have almost like those, like the last one I gave you, the simple one, which I thought was a gift with the mass, that a lot of people got wrong. They put 90 instead of 30. Remember, the mass never changes. There's going to be very few of those type of problems. But I do give you a couple problems, and I'm going to give you a warning now. Do you remember on the SAT or on like subject tests or standardized tests, you have these problems with Roman numerals? It's like Roman numeral 1, Roman numeral 2, Roman numeral 3. And the question will say, which of the following statements is true? And your answer choices would be 1 and 2, 1 and 3, 2 and 3, only 3, or only those kind of questions. We have to read a little bit. I'm going to give you a couple of those in this test just to give you a fair warning, kind of a preparation for the SAT subject test if you're going to take it. I haven't done that yet this year, okay? But you're going to see that happen from this test on, where I start to give options that are a little bit trickier because there's multiple Roman numeral choices there. But the math is rather straightforward. Here's literally the formula that you need to know. Oops. Okay, this is your one formula pretty much for the whole test. Everything comes from this. Everything comes from this. This is what we call the governing equation. If I've got motion in the beginning, I've got kinetic energy. If I've got height in the beginning, I've got potential energy. If I've got something that's stretched or compressed, whether it says it's a spring or not, if it's a rubber band, it's still a spring. In that case, I'd have elastic energy. So either I have potential energy, elastic energy, or kinetic energy. I can lose energy in a sense of losing, that's not the right word for it, but I can lose energy to thermal resultants or thermal interactions, which comes about from friction, and that always goes on the right side here. Okay, energy loss always gets tacked on to the right side. Why is that again? What's the reasoning for that? Why do we always tack it onto the right? Why not the left? I always put that Q loss on the right.
Is that because the final's going to be lost at that point? It's not going to be lost in the end.
Okay, that's a good way of thinking about it. You're losing the energy along the way, so at the end is when it's all lost. I agree. But mathematically, how about? Mathematically. If I start with a given number, give me a number. 40. So 40 joules of energy to start. Is that you, Clemence? Sorry. 40 joules of energy to start. And then at the end, you only have 35. Where did it go? The other 5 joules went to Q loss. The whole idea is that if you're going to lose, God bless you, if you're going to lose energy to friction, it's going to happen along the way, which will give you less energy at the end. So the compensation has to come into play with Q loss at the end. That's the missing 5, and that goes for Q loss. Okay? So Q loss is this idea that you can lose energy along the way. I can tell you what Q loss is. Maybe I tell you on the test tomorrow that the object loses 20 joules of energy on the way down. So this is going to be a 20 right away. You know that. Just put 20 joules in. But maybe I tell you instead that the work done by friction causes it, and the force of friction is 20 newtons. Well, then you need to replace this with the work done by friction. And that goes into play right there. And then if I tell you, oh, it's 20 newtons goes in here, if that's the force of friction. The given distance is how far it travels. Theta is 180 because it's friction. So it depends on the scenario how this governing formula will change. That's my gist. You had a question. Start with that, Noah. Is this a question?
Yeah, it's number 130 on
Page 224. So let's take a look at this one to start. All right. The problem says the following. Number 130. Here we go. A particle moves without friction. Right away. The first sentence, right? A particle moves without friction. What does that tell you right away? Without friction. without friction? What is not involved in this problem? Good. There's no Q loss right away, okay? It says without friction. At point A, the particle has a kinetic energy of 12 joules. So I might even just start like this. Call this point A, and say at point A, the kinetic energy is 12 joules. Then it says at point B, the particle is momentarily at rest, and the potential energy of the system is 25 joules. So if it's got potential energy, what must it have also? If it has potential energy, it has to have what? To have potential energy, you have to have, what am I doing? Why am I going like this? You got to have what, Marco? Height. So the second part, maybe we'll put object B or point B right here. And we're told that at that location, the potential energy is 25 joules. Then it says at point C, the potential energy of the system at point C is 5 joules. So it's got to be lower, right? At point C, it's got to be lower. So maybe I'll put it down here for now. And the potential energy is 5 joules. Now, at point B, let's write something down. It says at point B, it's at rest. At point B, it's at rest. Sarah? Very good, Sarah. This is the key. Without that statement, you can't finish this problem. The kinetic energy has to be 0 at the second location because it's at rest. What that tells me is the following. If I've got no kinetic energy here and 25 joules of potential, the total energy is 25. So if the total energy here is 25, how much is missing here? How much is missing here? 13. How much is missing here? Where are those energies? That's the missing type. So if 12 are kinetic to start, the 13 missing must be what kind of energy? It's got to be potential. So I don't know what those are, but I can start filling them in along the way because energy is conserved. Energy is conserved. The problem then goes on to say, what is the potential energy of the system at point A? Well, that's what we just talked about. What is the kinetic energy of the system at point C? That's what we just talked about. So because the sum of the energy is always constant, we can see that 25 is the total energy because of this statement. Without what Sarah contributed, we cannot solve this problem. Okay, this gives us the total energy here, which is 25, which means this total energy must be 25, which means this must be 25, which allows us to find the missing pieces. So since I'm trying to find the potential in the beginning, I can write that, and I think, okay, what plus 12, again, gives me 25? That's got to be 13. It's got to be 13. So these add up to 25. And then at the end, the kinetic that's missing at the very end has got to be 20. Okay, so these are your two answers that the problem is asking you about. Okay, but the theory is what I want you to understand. The theory that the energy is never gained or lost, it's only changed or transferred between potential and kinetic. Yes? Oh, but this is 130 I read out, sorry. But in the assignment it should be 103?
Yeah.
Did you do the wrong problem? Is that possible? Is 130 in the assignment for the problem set? You sure? Huh? You guys have it's on Moodle. Is it on?
Yeah.
What does it say? It says 103. It doesn't say 130. So just go back and look at 103. But hey, this is a great problem to look at anyway. Does it say 130? It's both of them, yeah. Maria, there's both, that's why. Okay? Yeah. So 130 is one of the problems, but 103 is another one of the problems also. Yeah. Okay, but even if this weren't one of the problems, this is a great example, right? Great example for especially like multiple choice. Does this involve math, really? Not much, right? It's arithmetic. It's simply adding. It's all theory. This problem is all theory. Do you see what I mean by that? The math is so simple that you could teach this to a second grader because it's only adding and subtracting. If they understood the theory as a second grader, they could easily finish this problem with just simply addition or subtraction. You don't need to solve an equation. You don't need to manipulate things. You don't have to solve for a variable. So this is not a math problem. You see what I'm saying? So expect a problem like this for multiple choice or short answer for sure. Yeah.
Can I ask another question?
Yeah. Of course.
What's the difference between throwing a ball up and throwing a ball up with like a rotation?
Okay. So we talked about this in the lab when we were talking about that day. Yeah. So his question has to do with the rotation of an object. So when you toss an object physically and you toss it with no rotation at all, it only has linear motion. It only has linear motion. But the minute I do this and roll it off, it has rotational motion, which takes some of that energy that you gave it into rotation.
Okay.
So by rotating it, some of my energy that I'm trying to give it goes into the rotation. So it's not getting as much energy as it would.
Oh, got it.
Okay? So you're kind of not losing, but some of it is being partitioned into the rotation. Whereas if I just tossed it normally, it's all going into the height that way. But this way, some of it goes into the height, some of it's the rotation. Notice how much harder I have to spin it? Because I have to give it more energy to get it up to that same height.
Doesn't it make the object move like in the axis?
The rotation? Sure.
Like is it like
Sure.
in one direction like makes
Yeah, so technically it would slightly move left and right. Yeah. But the idea is more about where the energy comes into play. But you're right. It would technically move a little bit left to right, but I wouldn't be concerned with that part as much. Homework or problem set questions that you've been A, stumped on, B, want to go over. That's what I'm kind of opening up the floor for first to start. Ed, I'm going to come back to you because you asked the first one, and then we'll come back. Ed? I got it. Same section, right?
Yes.
Okay. So number 100 says, where are we? There we go. 3 balls are thrown upward with the same initial speed. So this is going to be theoretical, not really math, okay? With the same initial speed, V0, or VI, what they call it, but at different angles. So we have 3 objects. One looks like this, being thrown straight upward. The second one is being launched at an angle like this. And the third is being launched at a lower angle. Ignoring air resistance, indicate which of the following statements is correct when the ball is at the dashed level. So here's the dashed level in the diagram. So the first one reaches it here. The second one continues to reach it there. The third one reaches it over here. And then they're all going to kind of fall in a parabolic manner. All right, so it says which of the following is correct when the ball is at the dashed level. So this is ground level right here in red. Okay, this is ground level right here. It gets up to this height right here. Before I even look at the choices as possibilities, I think this has kinetic to start, right? At the top of this path, what kind of energy does it have? At the top of the path here, what kind of energy? Potential only, right? And then it comes back to kinetic when it falls back down. But what about the other 2 paths? How do they differ? How do they differ? There is a difference. It has an angle, agreed, so? You could use VI cos theta and VI sine theta to find the components, sure, but we're looking at energy right now, right? So let's just think energy-wise. In the beginning, what kind of energy does it have? In the beginning, because it's being launched with velocity, what kind of energy does it have? On the ground? Kinetic. Remember, when it's on the ground, it can't have potential ever. So in the beginning, it can't have potential here. It's being thrown with some velocity, getting a kinetic motion, right? The question becomes, what about these locations then? What kind of energy does it have at these locations?
Why are there like second arrows?
It's just me extending the diagram. I'm in the middle of a question, Peter. Come on. You just wait a second next time. At this point in time, when it reaches the top, what is the difference between this one right here?
Those 2 aren't just fully potential energy because they're spread among kinetic and potential.
Why do they still have kinetic? He's right. He's absolutely right. It's not like here it was all potential. Here it was all kinetic, right? But at this point it's going to be both potential and kinetic. Even if it's at max height, even if it's coming back down, it's still both potential and kinetic. Maybe it's going to do this and come back. Maybe this one will do this and come back. It can still be max height. Why are there both potential and kinetic in these spots, Chris?
Because they moved in the x-direction.
Yeah. What did you remember from kinematics? When an object reaches the top, it stops, right? Vertically, it stops. But it's always moving horizontally if it was launched at an angle. So even at the peak there, at those instances in the peak, you still have kinetic energy here. Whereas in the first part, you only had potential because it was only thrown straight upward and it actually physically stopped for a moment in time. But when it's still moving horizontally in these two cases, it still has kinetic energy at the top. But for all 3 cases in the beginning, there's only kinetic energy. So this is the way I'm interpreting it. Let's look at the statements, okay? So it says the following. Which is true when the ball is at the dash level. The first thing says ball 3 has the lowest speed. Ball 3, which is the third path, has the lowest speed. The second statement says ball 1 has the lowest speed. Ball 1 has the lowest speed. The third statement says all 3 balls have the same speed. And the fourth statement says the speed of the balls depends on their mass. Based on what we've said so far, do any of those stick out right away? One of them jumps out to me right away, based on what we've drawn at the top. Again, statement 1, ball 3 has the lowest speed at the top. Statement 2, ball 1 has the lowest speed at the top. Statement 3, all 3 of these have the same speed. Statement 4, the speed depends on the mass. Which of those seems to be the most true? Or which jumps out at you as being true?
I said D.
D. The ball speed depends on the mass. Think about you asked me during lunch a minute ago. Remember what I talked about? When there's no springs and a Q loss involved, what drops off every time? So does it depend on the mass? It's not D. I like the idea though, you want to think it depends on the mass, but it doesn't, it turns out. Maria, what do you think?
Is it D?
Why B?
Because it's like PE at the top.
So what's the speed at the top? What is it physically? What is it? If it's, hey, Mark is 0, it stops, right? So it says for part B that ball 1 has the lowest speed at the top, and it does. There's no kinetic energy here because it stops. So the lowest speed possible is 0, isn't it? That's physically the lowest speed you can ever have. Not velocity, but speed. Velocity, you can have negative velocities, right? But speed, the lowest it can ever be is 0. That's this case. Okay, so it would be choice B, and that's the rationale behind it. Okay, that's the rationale. That was example 100. Others, you had a hand. Anyone else? Go back to you, Noah. Go ahead.
Another conceptual one, number 109.
Oh, sorry. You want to? I got it. Okay. All right. Number 109, conceptual with power. Okay, so this is from 6-4 about power. So what are we thinking right away? If it's about power, we're looking at energy as a function of time. How fast you absorb, use, dissipate, give off, any of those words, energy. How fast you do it. That's what we're talking about. It says engine 1 produces twice the power of engine 2. Does that statement make sense so far? The power produced by engine 1 is equal to twice the power produced by engine 2. That's how I start thinking about it. It says if it takes engine 1 the time T to do work W, how long does it take engine 2 to do the same work? So you don't really need math. That's why they give letters, right? But you can pick numbers if you want. You can always pick numbers. It says if it takes the time T, call that 2 seconds. To do work W, call that 20 joules of work. But the question asks, again, that it takes engine 1 a certain amount of time to do a certain amount of work. That's the power from engine 1. Now, if I compare these two, if the second machine, right, if the first machine has twice the power of the second, what does that physically mean to you? If you have more power, or you can generate more power, what are you physically doing?
You have more work.
You're doing, careful, you're doing more work, or you're doing work, what's the word?
Wait, I was going to say you're doing more work over a shorter period of time.
Good. So it's either you're doing more work, or you're doing the same work in a shorter period of time. Agreed? To have more power, you can either do more work, or do the same work as the other object, but do it quicker. Okay? Now, it says here that we want to do the same amount of work. It says if the engine in the first one takes time T to do work W, how long does it take the second engine to do the same amount of work? So the amount of work isn't changing, yet the power is twice the other one. So what has to be changing then if the work isn't changing? Time. Okay, so if I do the same amount of work as Chris, but Chris has twice the power I have, Chris is doing his work twice as fast as me. So if it takes a time T for this to happen, it would take this one twice as much time because this one has twice as much power. Okay, so if an object or a machine is twice as powerful, it simply means it can do the same work as the other machine twice as fast. Right? Twice as fast, or in half the time. In half the time. Because time and power are indirectly related. So to do have twice as much power means you're using half the time. Twice as much power means you're going to be using half the time possible. Half the time. What else? What else? Other homework questions or concerns or even questions out of the notes you've struggled with? M?
Just other things that we should know, like the conceptual part.
Other?
Conceptual thing.
So we've alluded to a lot of the conceptual in the math problems. So for example, recognizing that motion refers to kinetic energy, height refers to potential, anything stretched is elastic, right? Recognizing that energy is always conserved, so at any point along the way, you should have a total that's the same. That was the kind of first example we did. Thinking about what work is a function of. To do work, you have to apply a force over a distance. So, answer the question for me. Am I doing any work right now? Am I doing any work, Maria? How come? I'm not moving. Very good. Sure, it takes me some strength. I have to physically apply a force. The force is in your muscles in your body that's able to hold a marker up, right? But I'm not moving the marker. The minute I do this, now I'm applying a force over a distance and I'm doing work. I could hold it right here all day long, above my head. I'm doing no work. It hurts. It's annoying. If you have a bad shoulder, it definitely hurts, like me. But you can hold it here all day long and you're not doing any work. Okay, you're doing no work whatsoever. Trying to think theoretically. Recognizing the parameters that affect things. So if I said to you hypothetically, this is a good sample question. If the mass of an object doubles, what happens to its potential energy? It should be very straightforward and simple, but think about the formula for potential energy. If the mass doubles,
It would increase
by
by
a factor of
2.
2. If it doubles, right? So if I double the mass, I have double the potential energy. Now let me follow up with a more difficult one, okay? If the mass of an object doubles and its velocity triples, mass doubles, velocity triples, what happens to its kinetic energy? And I say kinetic because I'm talking about velocity now, right? If the mass doubles and the velocity triples, what happens to its kinetic energy? Got it?
Triple?
It's a little more complicated. There's 2 steps to this problem. The mass doubles, the velocity triples, what happens to the kinetic energy?
It increases.
By a factor of? It's going to increase for sure, yeah. The question becomes by what factor? Think about it mathematically. Use an example if you have to. Go ahead and use an example right now. Prove to yourself. Call the mass 1, call the velocity 1, and then double it in the next scenario for the mass, and triple the velocity and come up with a new energy. See what they are. Compare the two. Literally, go ahead and do that. 1/2. Use 1 for the mass, use 1 for the velocity, and then for the second case, double the mass, so use 2, triple the velocity, so use 3. Get an answer for both of those kinetic energies and compare them. See by how much does it go up, by what factor. I'm going to do that on the board so you can see it as we do it, but I'm going to show you another way to do it that's, I think, easier. But so I want you to see numbers first if we don't understand it. So let's say initially this was our kinetic energy. 1/2 mv squared. But then I double the mass, so this will end up being an answer of 1/2. But then the second one, so we'll call this the new, we'll call that old. The new kinetic energy has double the mass and triple the velocity. Goes up by? Not 4. Not 4. It's trickier than that. What's 1/2 times 2 is just 1, times 3 squared gives me 9, right? Gives me 9. How much did it go up by?
By 18.
By 18. 18. Where the heck is he getting this number?
Chris, what did you
What'd you do?
Did I do it wrong?
No, you're right. Absolutely right.
Okay, good.
How'd you get it?
I just like took two different like values and then like I plugged in like m equals 1 and b equals 2.
Agreed.
And solved that.
Agreed.
2, and then doubled the mass.
Go ahead, keep going. At the end, what did you do, Chris?
I got 36. I just like, and then
So what was your first answer then? 4?
I
No.
divided them. I divided 2.
Thank you. So you took your new one and you divided it by your old one, right? So take the new energy method or new energy amount over the old energy and you'll get 18. Write this down if you don't know this. I talked about this in class. I said specifically, factor of increase is or decrease is always looking at the ratio between the new and the old. The new and the old. If tomorrow, hypothetically, I gained 150 pounds, I would have doubled my weight. I weigh around 150, let's say. So I would have doubled my weight because I look at the increase of 300 divided by 150. Okay, be careful. The common mistake, and I'll tell you right now, hint, okay, and it's usually a choice. If it's multiple choice, this will be multiple choice. It's not very much math. 9 and 1.5. What do you think the common mistake is to give us an answer?
3.
Why 3?
Because you have.
Because you what? Careful.
Okay, never mind.
Not 3. It could be 4.5. I can see that. Taking half of 9 to 4.5. I'm thinking of a different one. That's okay. Guys, please, don't worry. It doesn't matter. You don't have to be right or wrong. What else? What do you think the other common mistake is? If it's not around, then maybe I shouldn't even discuss it, because I just feel like it comes up a lot. Yeah. I think most people subtract them. They say, oh, we had 9 joules, or we had a half a joule, and now we have 9 joules. 9 minus a half is 8.5. So let me make this statement. The energy went up by 8.5 joules, but it increased by a factor of 18. Again, the energy went up by 8.5 joules. That's physically how much it increased by as a number. But the factor, keyword factor of increase is the new divided by the old, 18. Now, you might ask yourself, do I want to try numbers every time? I don't want to try numbers every time. And as a science teacher, I definitely don't want to try numbers every time. I want to come up with an algorithm that will work better than this. So instead, here's what I do. And this might be useful. Some of you might like this. I think about my formula for kinetic energy. And I say to myself, I'm varying the mass and I'm varying the velocity. So let's go ahead and write out the kinetic energy formula. Right? Here's what it is. Boom. That's the kinetic energy. But now vary everything. Double the mass. So replace mass with 2m. Triple the velocity. Replace that with 3v. Now, take a look. 3v as a quantity squared becomes what? This is where your laws of exponents come into play a lot. If you square a product, what does the answer become? 9v squared. You have to square both, right? So that goes up by 9. This goes up by 2. 9 times 2 gives you an increase of 18. It's a much easier way to do it than plugging in numbers. So take a look at what I'm going to write just to show you. So this is like my old. This is my new. And I just want to simplify new a little bit further. If I'm going to simplify it, I'll leave the 1/2 in front. I still have the 2m. 3v quantity squared is really 9v squared. See how the squared moves? See how when I distribute it, it moves inside? And this 2 times this 9, right here and here, is the only difference. These two spots are the only difference between this formula and this one. So I multiply by 2, I multiply by 9. Everything else is the same. 2 times 9 gives me the factor of increase from over here, which is 18. It's another way of taking a look at this problem. And if it helps you, some students in the past like to do this. And they write 1/2 mv squared times 18. That's physically what's happening. Take the 2 and the 9, put it at the end. How come I'm allowed to do that? Multiplication is commutative. Okay, I can take a 2 and a 9 and reorder it and move it out front. It's also associative, which allows me to take it outside the parentheses. The idea, though, is that this is the same as 1 half mv squared, but with an 18 included. That's the factor of increase right there. A lot easier, I think, than actually plugging in numbers and having to divide and do the math. I would just replace the variable with what it increases by and then simplify as far as possible. This was the old kinetic energy, 1 half mv squared times 18, which means it went up by a factor of 18. Okay, that's like another conceptual kind of problem. This you could expect as like a multiple choice question because it doesn't involve math actually. This is making it involve math. You don't need any numbers. You don't need them. This is all you have to do. Somebody asked me yesterday a question and I responded with, well, the question was, can we really try to use the formulas to help answer a lot of questions? And the answer is absolutely yes, and you should. I highly recommend that whenever you can answer a question that's theoretical, the middle part, not the multiple choice too, also. But the middle part that's theoretical, use a formula that helps to explain the theory that's happening. So if I'm asking about work, look at the work formula. If I'm asking you about kinetic energy in the problem, look at the kinetic energy formula. It will help you to understand the physical nature of the problem. Okay, it really will. And use your formula to help explain things. Go ahead.
Explaining like part of it, is it government questions like that, like explaining like the kinetic formula, like math and all that, or is it gonna be more like problem based? Like last time it was like like the bucket thing.
Yeah. I mean, it could be either of those, honestly. I don't want to hint you in one direction or the other and then it appears. I haven't even written the test yet, so to be honest, it's Wednesday. The test's not till Friday. But in the past, on the test, I'm thinking in the back of my head in the way I've given this test before, you'll definitely be asked things that involve explaining some unbalanced number. For example, hypothetical question. You know, a problem starts where an object is fired from a cliff and it has 20 joules of kinetic energy and 30 joules of potential to start. So that's a total of 50 joules. At the end of the problem, the object has only 45 joules of kinetic energy. Explain the discrepancy. Where did the 5 joules go? Well, on the way down, if you lost energy, it must have been to some sort of air resistance or friction, discussing how you lose energy along the way because of that. Or a problem that says the energy in the beginning is 27 joules, the energy at the end is still 27 joules of potential and kinetic. What can you conclude? There must have been no friction in the problem because you have the same that you started with. So those kind of questions come to play a role, but I don't know. I don't want to give you a direction in that sense and say one's better than the other. What else? Homework questions. I'm trying to think of other tough questions that we didn't get to go over either in class or in notes. Yeah.
It was from the homework from 6-4.
Okay.
Number 57 on 216.
Okay.
It was just,
What is the power output of a 1.4 gram fly as it walks straight up on a window pane at 2.3 centimeters per second? This is a great question, okay? So the fly has to overcome its own weight to walk up. Here's the fly, right? And it simply goes up a little bit at a time. The only way for a fly to climb up is to counter its own weight. So the amount of force that the fly has to push with is equal to its own weight. So you're given the mass of the fly. The mass of the fly is given as 1.4 grams, which is equal to 0.0014 kilograms. So there's the mass of the fly. We're told that its speed is 2.3 centimeters per second, which equals 0.023 meters per second. So the conversion is the beginning part you have to consider, right? Now you're given a speed, you're given a mass. Power, though, if you recall, is equal to force times speed if I'm going to use that formula, not mass. So if I have the mass of the fly and I want to find out how much force it needs to apply, I need to find out the weight of the fly that it has to push against every time it climbs up. How do you find weight? Weight is mass times gravity, mg. So this is really the weight that it's applying to counter its actual value. So the power is really just mass times gravity times speed. Okay? You got mass, gravity is 9.81, and you got speed right here. Okay? Yeah. What do we have? This is a homework question. Homework number 57 on page 216. Yes.
Are there going to be like the practice problems you put up?
So what I did, Em asked me this earlier. Last year I recorded 3 long examples of problems, or 2 years ago. I don't have any practice problems honestly made or even written for this, and I really don't have time to do it right now, but I have a video with 3 other problems that are examples from the old textbook that we used to use. So the video recording is there, and it explains the problems, but I need to put up the questions still. I took pictures of them in the old book. I'll put those up. So it's 3 samples. But honestly, if you're looking for more problems, I'll tell you where to look. If you look at the end of the chapter on those questions like number 130 that we looked at, there's a bunch of good examples. Even something like number 142 is a good example. Number 141 is a good example. Number 138 is a good example. So those are just, I'm honestly looking at these sets of questions. So feel free to look through some of these. Anything that involves changing of energy would be useful. If you see that it goes from potential to kinetic or resting with power, these are mixed problems. Some of them could be a little more difficult than others though at the end. But those are 3 good examples. But feel free to just kind of peruse and maybe come ask me if you want. Yes?
Can you go over on the slide 6.3 example
6.3 example 5. Can I just look at it? Ooh, I like this problem. Okay, yeah. So an object with a certain mass is slid across the rough surface of a lab table. If it starts moving due to a spring that was compressed and then released, so this is like a pinball machine. Pinball machine is the good example for this. The object starts moving. How far will it have traveled when it's moving with the speed of 4 meters per second still? So let's take a look at this kind of a problem. So if it's compressed in a spring to start, okay, there's the floor, and then suddenly you let go of that spring, and then the object gets launched in this direction. That's what we're physically seeing, okay? Now, it has nothing to do with changing height. It says nothing about changing height. It says a rough lab table. So a lab table has the same height the whole time. So is there any potential energy change anywhere? No. The potential energy is 0 at all times because it's on the ground. Now, if it's compressed in a spring, it's got elastic energy to start. Later on, it's going to be moving still. The question said it's a rough surface. So what are we assuming there's going to be? Friction. Very good. So it's going to lose some energy to friction along the way. And then at the end it says, find out how far it's gone, d, the distance. Find out how far it's gone if it still has a velocity of 4 meters per second. If it still has a velocity, what does it still have then? If it still has velocity at the end, it still must have kinetic energy. So here's your problem right here. That's literally the whole problem. The hardest part is that. And now it's just math. Everything is just algebra at this point. So let's go ahead and look. Initial equals final. I'm not even going to use numbers, okay? I don't even know what the numbers are. I'm going to ignore them for a while. Initial equals final. Initially, the energy is stored in the spring. It's still moving at the end, so it's got kinetic at the end. It loses energy along the way, so we put a Q loss here. So you see how I'm progressing through the equation? Governing, still the same. MEI equals MEF, always. Then we progress through. Now, formulas have to come into play. 1/2 kx squared. 1/2 mvf squared. Q loss could be many things. It could be given to you as a number. If Q loss is 12 joules, you just plug it in. But here it asked about how far did it travel in distance. And what is Q loss usually? The work done by? Yeah. Work done by friction is FF times D times cos theta. That's the work done by friction. So in a problem that you're trying to find out how far it has slid across the ground, by the way, extra credit, still open till Friday. Only till Friday, though. It's not in by Friday. It's not counted. Remember the sliding of the socks across the floor? You got to measure yourself and figure that out. Consider that. It's bonus points for the test. Nobody's done it so far. So this is pretty much the problem with the sliding across the floor, except instead of a spring, you're not attaching yourself to a spring and getting shot out. You're actually running and sliding with a given initial velocity. So this would be 1/2 mv squared for that one. Now, because this object is still moving at the end of the problem, we have velocity still. In the extra credit, you're going to come to the rest at the end, so this won't even be there. And you'll just have this right here, with this as being kinetic. But this problem is different. The question asks us how far it's going to travel. What variable represents how far it'll travel? How far it'll travel. Peter?
D.
D. Very good, and not x. Some people think x right away. What is x in this equation? X in other equations is something else. What's x in this?
Isn't it the stiffness?
Careful, that's k. K is that. Help her out. How far the spring has been compressed, or how far the spring has been stretched. Okay, k is the stiffness itself. So yes, x in this case would be our change in length, whatever that turns out to be. It really doesn't matter what the number is. What problem was this again, guys? What was it? Oh, it's in the notes. That's why I'm trying to look at the numbers in here. So our goal, though, is to figure out the distance traveled. I don't have FF. Everything else is given in this problem. I'm given a spring stiffness. I'm given the mass. We're given the velocity at the end. We're given how far the spring is stretched. We're looking for D. Theta is 180 because it's friction. So we're looking for D. We need FF. What's FF? FF equals, what's the formula from last chapter? FF equals, mu k times Fn. In this case, it's k because it's kinetic. But Fn for this problem is mg. Remember, Fn is mg a lot because of the fact that there's no vertical forces acting. So FF is mu k mg. So replace this with mu mg and then continue the problem down. Okay, definitely a good example to look at for tomorrow, for Friday's test. Okay, everything's given. Mu is given, M is given, G is given, theta is given, D is what you're looking for. Solve for D. Plug in all the numbers everywhere else, right? Plug in all the numbers and then solve for D at this point. Hey, please, listen. Come tomorrow after school or come during a free. I'm not here today after school. I mentioned this yesterday to you guys for that reason. Okay, I'm not here today after school, but tomorrow I am, or tomorrow during a free period. Please, if you have questions, ask me. I only saw like 3 people this morning, which was a little upsetting because we have a big test.
I do have a quick question. How do you know what is the what's theta in the problem? Like, how do you know that's 180?
So it's either 180 or 0. Because when I move this way, which way does friction act?
The right.
If I move this way, friction acts.
Oh, to the left.
So what's the angle between these?
180.
So whenever it's friction that's doing the work, whenever it's Q loss from friction, it's always going to be 180.
Oh, okay.
But if it's work done by pulling something, if you're pulling it this way and it's moving this way, the angle is 0. Because this is one vector of direction, this is your vector of pull, the angle is 0 between them.
Okay.
So it just depends on what you're looking at.
So if it involves direction, then it's 180.
Correct.
Thank you.
You're welcome. Thanks. Yeah. Steve, I'll give you credit. It's fine. I just checked that you did it, so just hold on to it. I just want to see that you've done it. Thanks. I heard there's another math club competition tomorrow morning. Aren't you part of the math club? How's that going to go? Yeah?
I've been doing well this year.
You have not? Oh, I was going to say. Is it fun? Are the questions cool?
I like that.
They're very interesting, right?
Yeah.
Make you think outside the box?
It's not like class. There's like several types of questions. All we're going to deal with is also like
Anything, right?
Yeah, anything.
Yeah, and you might combine topics in there too. Very cool.
not like strictly
I did that in middle school and high school. Like, I was on all that. We had like teams. We would go to compete. You had to go to schools, and you would even have buzzing in and stuff.
Oh, that's so. I used to do that when I was like
Like an Olympiad.
It gets so intense in the end.
They get real intense.
Yeah, but it's really fun.
Isn't it?
Yeah.
Hey, listen, guys, listen. Don't make Mr. Donachek yell. His voice is gone. So make sure you behave today. Don't make him raise his voice at all. Seriously, his voice is like gone. He came in just to make sure he teaches us. So from hell is over. The day from hell is over. Dude, next year maybe we'll put Science Club on a different day if our schedules are shitty. Because I would not do this again if I had a choice. I'd make it day 4 and just say, you know what? Fuck all the other clubs that keep screwing us over anyway, you know? But I did notice, I love how certain people are so intuitive or they notice things. Holden has noticed that we do a half period thing now. You notice that? So she's been doing a lot of her lessons or her club meetings where it only starts halfway through. And she's like, oh, you know what? Other clubs are doing that. We should probably do the same thing to be fair, you know? And it said it will only take place during the first half of the activities period of the announcements, which I'm like, oh, shit. But somebody like her would know, or somebody like she would notice it, but others would, you know, completely overlook.